Have you ever wondered if reality behaves in unexpectedly different ways depending on how it is observed before deciding what it wants to be? In the quantum world, particles exist in what scientists call superposition, essentially being in multiple states simultaneously, until the very moment someone observes them. Then, in an instant that defies everything we think we know about how the world works, they collapse into a single, definite state. It's as if the universe itself is playing an elaborate game of hide and seek, where the outcome remains undefined until measurement reveals one possibility. Welcome to a gentle exploration of one of the most puzzling mysteries in all of science. I'm here to walk with you through the strange landscape of quantum mechanics, where the very act of observation seems to reshape reality itself. Tonight, we'll drift together through the implications of what it means to live in a universe that apparently responds in surprising ways when it is measured. Before we begin this journey, let me invite you to settle in wherever you are. Perhaps you're curled up in bed, headphones on, ready to let these ideas wash over you like waves on a shore. Maybe you're walking through a quiet evening, the stars above carrying their own quantum secrets. Wherever you find yourself, know that you're about to encounter ideas that will shift the way you see everything around you. The story we're about to explore isn't just about particles and wave functions. It's about the fundamental nature of reality and our place within it. It's about the mysterious boundary between the world of the very small, where nothing seems to follow the rules we take for granted, and the world we inhabit, where chairs are chairs and trees are trees. Picture this: it's the early 1900s, and physics feels almost complete. Scientists believe they understand how light works, how matter behaves, and how forces interact. The universe appears to be a vast, predictable machine where every cause leads to a specific effect. Then comes a simple experiment that shatters this comfortable certainty forever. The double-slit experiment sounds almost boringly straightforward. You take a barrier with two narrow openings and shine light through it onto a screen behind. What you see should be two bright lines corresponding to the light passing through each slit. But that's not what happens. Instead, you get something far more mysterious: a pattern of alternating light and dark bands spreading across the screen. This interference pattern can only be explained if light behaves like a wave, spreading through both slits simultaneously and interfering with itself on the other side. The wave peaks amplify each other, where the bands are bright, while peaks and troughs cancel each other out, where the bands are dark. Strange, but scientists could accept this. Light as a wave wasn't entirely new, but then they tried something that would haunt physics for over a century. They dimmed the light source until only one photon, one particle of light, passed through at a time. Logic suggests that each individual photon should go through one slit or the other, creating two simple lines on the screen. But the interference pattern persists. Somehow each single photon appears to go through both slits at once, interfering with itself to create the same wave-like pattern. It's as if each particle of light exists in multiple realities simultaneously, exploring every possible path until it reaches the screen. This is where the story takes its most bewildering turn. Scientists decided to place detectors at each slit to determine which path each photon actually takes. The moment they do this, the interference pattern vanishes. The photons start behaving like ordinary particles again, going through one slit or the other, creating two simple lines on the screen. It's as if the system changes its behaviour the instant measurement enters the picture. Take a moment to let this sink in. As you contemplate this idea, Notice how it challenges everything you might have assumed about the nature of reality. The very act of trying to peek behind the curtain changes what's happening behind the curtain. What we're witnessing in that moment of observation is something physicists call wave function collapse. Before measurement, the quantum system exists in what's known as superposition, a ghostly state where all possible outcomes coexist simultaneously. The mathematical description of this state, called the wave function, contains the probabilities of finding the system in any particular state. But here's where it gets truly strange. The wave function isn't just a description of our knowledge about the system. According to quantum mechanics, it represents the actual physical state of reality before observation. The photon genuinely exists in a superposition of going through both slits until the moment someone looks. The collapse happens instantaneously. One moment, the particle is a cloud of possibilities. The next, it's a single, definite reality. This isn't like flipping a coin where the outcome was determined by the initial conditions. We just didn't know which way it would land. In the quantum world, there genuinely was no predetermined outcome until the moment of observation. This phenomenon extends far beyond photons and slits. Electrons can exist in superpositions of different energy levels. Atoms can be in multiple locations simultaneously. Even relatively large molecules have been shown to exhibit quantum superposition, existing in multiple states until measured. Scientists have pushed these boundaries further and further. They've created superpositions with molecules containing thousands of atoms, systems that by any reasonable standard should behave according to classical physics. Yet even these larger systems maintain their quantum nature until the moment of observation. But what exactly constitutes an observation? This question has puzzled physicists for nearly a century. Does it require a conscious observer, or is any interaction with the environment sufficient? The answer turns out to be more subtle than either extreme. The measurement problem, as physicists call it, strikes at the heart of our understanding of reality. When we say that observation causes wave function collapse, what do we really mean by observation? Early interpretations of quantum mechanics, particularly those developed by Niels Bohr and Werner Heisenberg in what became known as the Copenhagen interpretation, suggested that the act of measurement was fundamental to quantum mechanics. They argued that quantum systems don't have definite properties independent of measurement. The properties we observe are created in the interaction between the quantum system and the measuring device. But this raises profound questions. If measurement is so crucial, what distinguishes a measurement from any other interaction? When you look at a quantum system, photons from a light source bounce off the system and enter your eyes or a detector. This interaction disturbs the system, potentially explaining why its behaviour changes. However, the story isn't quite that simple. The disturbance caused by measurement doesn't fully explain quantum behaviour. Even when scientists design experiments to minimise this disturbance, the fundamental mystery remains. The quantum system still behaves differently when measured versus when left alone, regardless of how gently the measurement is performed. Some interpretations have suggested that consciousness itself plays a role in wave function collapse. The idea is that the universe remains in superposition until a conscious mind observes it. This interpretation gained some following among early quantum physicists, though it has largely fallen out of favour in mainstream physics. The consciousness-based interpretation leads to peculiar paradoxes. If consciousness is required for wave function collapse, what happened to quantum systems for billions of years before conscious beings evolved? Did the entire universe exist in a state of superposition, waiting for the first mind to observe it? Most physicists today favour explanations based on environmental interaction rather than consciousness. In this view, quantum systems lose their superposition properties through interaction with their environment, a process called decoherence. The environment effectively acts as a constant measuring device, continuously interacting with quantum systems and causing them to behave more classically. As you consider these different possibilities, you might find yourself wondering about the nature of your own observations. Every time you look at something, light bounces off it and enters your eyes. It raises the philosophical question of how everyday perception relates to what physicists describe as measurement. One of the most startling aspects of wave function collapse is its apparent instantaneity. When a measurement occurs, the collapse happens everywhere. The quantum system exists simultaneously, regardless of how spread out it might be. This seems to violate Einstein's principle that nothing can travel faster than light, including information. Einstein famously called this spooky action at a distance when discussing quantum entanglement, a related phenomenon where particles become correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. He couldn't accept that the universe would allow such seemingly instantaneous effects, but experiments have consistently confirmed that quantum correlations do indeed appear to operate instantaneously across arbitrary distances. When two particles are entangled and you measure one, the other immediately responds, even if it's on the opposite side of the galaxy. The correlation happens faster than light could travel between them. However, this doesn't allow for faster than light communication. While the correlation is instantaneous, you can't use it to send messages because the results of quantum measurements are fundamentally random. You can't control what outcome you get when you measure your particle, so you can't encode information in the measurement results. This randomness is another crucial aspect of quantum mechanics that distinguishes it from classical physics. In classical physics, randomness usually reflects our ignorance of the complete state of a system. If you knew the exact position and velocity of every molecule in a coin when it was flipped, you could predict whether it would land heads or tails. But quantum randomness appears to be fundamental. Even if you knew everything possible about a quantum system before measurement, you still couldn't predict with certainty what outcome you would observe. You could only calculate the probabilities of different outcomes. This fundamental randomness troubled Einstein deeply. He felt that a complete theory of physics should be deterministic, leading to his famous declaration that God does not play dice with the universe. But experimental evidence has consistently supported the quantum view that the universe does indeed appear to play dice at its most fundamental level. The combination of instantaneous collapse and fundamental randomness creates a picture of reality that's both deeply strange and strangely beautiful. It suggests that the universe is not a clockwork machine running according to predetermined laws, but something more fluid and responsive, where possibilities crystallize into actualities through the mysterious process of observation. Take a breath and consider what this might mean for your experience of reality. Every moment, countless quantum events are occurring around you and within you. Each observation, each interaction, each moment of awareness might be shaping how you encounter and interpret the world around you, rather than altering the world itself. This brings us to one of the most profound implications of quantum mechanics, the idea that we live in what physicist John Wheeler called a participatory universe. Wheeler suggested that reality is not something that exists independently of observation, but rather emerges through the act of observation itself. In Wheeler's view, the universe is not a collection of objects with predetermined properties waiting to be discovered. Instead, it's more like a vast web of potential outcomes that become real through interaction and observation. Every measurement, every observation, every act of gaining information about the quantum world participates in bringing that world into existence. Wheeler proposed thought experiments to explore this idea further. In his delayed choice experiment, he imagined scenarios where the decision about how to observe a quantum system could be made after the system had already interacted with the experimental setup. Remarkably, when such experiments were actually performed, they showed that the choice of measurement could indeed seem to retroactively determine what had happened in the past. This doesn't mean that the past is literally changed, but rather that the past, present, and future are more interconnected in quantum mechanics than our everyday experience suggests. The properties we observe in quantum systems may not have been fully determined until the moment of observation, even if that observation comes after what we would classically think of as the system's journey through the experiment. The participatory universe concept challenges our usual notion of objectivity in science. We typically think of scientific observation as passive, revealing truths about a world that exists independently of our investigation. But quantum mechanics suggests that the boundary between observer and observed may be more fluid than we assumed. This doesn't mean that reality is subjective or that we can change the laws of physics by thinking about them differently. The quantum world still follows mathematical laws, and those laws make precise predictions about the probabilities of different outcomes. But it does suggest that the relationship between mind and matter, between consciousness and cosmos, may be more conceptually intertwined than classical physics once assumed, without implying any direct influence of thought on physical systems. As you listen to these ideas, you might find yourself questioning the nature of your own observations and experiences. When you look at a star in the night sky, are you simply receiving light that left that star years ago? Or are you engaging with a perspective that highlights how observation shapes our experience of the cosmos, including both you and that distant sun? The implications of the observer effect extend far beyond physics laboratories. They touch on fundamental questions about the nature of consciousness, the relationship between mind and matter, and our place in the universe. While we must be careful not to overextend quantum mechanics into realms where it may not apply, the phenomenon does invite us to reconsider some of our basic assumptions about reality. One area where quantum mechanics has begun to inform our understanding is in the study of biological systems. Researchers have discovered quantum effects in photosynthesis, where plants appear to use quantum superposition to efficiently channel energy from sunlight. Bird navigation may rely on quantum entanglement in their visual systems, allowing them to see magnetic fields. Even the sense of smell might involve quantum tunneling effects. These discoveries suggest that quantum mechanics isn't just an abstract theory relevant only to physicists. It may be operating all around us and within us, playing a role in the very processes that sustain life. The boundary between the quantum and classical worlds may not be as clear-cut as once thought. Some researchers have even explored whether quantum effects might play a role in consciousness itself. While this remains highly speculative and controversial, the idea that the brain might harness quantum processes for information processing offers an intriguing possibility for understanding how consciousness arises from matter. However, it's important to approach such ideas with appropriate caution. The brain is a warm, wet, noisy environment where quantum effects typically last for incredibly brief periods before being destroyed by environmental interference. Most neuroscientists believe that classical physics is sufficient to explain brain function, though the question remains open to investigation. What's less speculative is the way that quantum mechanics challenges our everyday intuitions about causality, locality, and the nature of information. These challenges have philosophical implications that extend far beyond physics, touching on questions that have occupied thinkers for millennia. The observer effect suggests that the act of gaining knowledge about a system can change that system in fundamental ways. This has parallels in other fields, from psychology, where the act of observing behaviour can alter that behaviour, to anthropology, where the presence of an observer can change the culture being studied. In your own life, you might notice similar patterns. The act of paying attention to your thoughts can change those thoughts. The process of examining your emotions can transform them. Self-awareness itself seems to alter the self that's being observed. These parallels don't prove that consciousness operates according to quantum mechanics, but they do suggest that the relationship between observation and reality may be more psychologically and philosophically nuanced than classical physics suggested. The quantum world offers a metaphor, at the very least, for understanding how awareness and reality might be more intimately connected than we typically assume. As we continue our exploration of this quantum paradox, we'll delve deeper into what these discoveries might mean for our understanding of consciousness, reality, and the mysterious relationship between the two. We'll examine the various interpretations that physicists have proposed to make sense of these phenomena, and we'll consider what it might mean to live in a universe where the very act of observation plays such a fundamental role in shaping what we observe. The journey we're taking together is one of wonder and questioning, of opening our minds to possibilities that challenge our most basic assumptions about how the world works. As we move forward, remember that you're not just learning about quantum mechanics, you're participating in the ongoing human quest to understand the deepest nature of reality itself. Let's drift deeper into this mystery, where each step reveals new layers of strangeness. As you settle into these ideas, notice how they might be shifting something in your own awareness, the way a gentle current can change the direction of a leaf floating on water. The quantum world doesn't just challenge our understanding of particles and waves, it questions the very foundation of what we mean when we say something exists. In our everyday experience, we assume that objects have definite properties whether we're looking at them or not. Your coffee mug has a specific temperature. Your phone has a particular location. The tree outside your window has a certain height. But quantum mechanics whispers a different story. It suggests that at the most fundamental level, properties don't exist independently of observation. Instead, they emerge from the interaction between the observer and the observed, a relationship some interpretations use as a metaphor for how measurement influences outcomes. This isn't merely a philosophical curiosity. Experiments have confirmed this strange reality again and again. When scientists prepare identical quantum systems and measure different properties, they get results that are fundamentally incompatible with the idea that all properties existed simultaneously before measurement. It's as if the universe is telling us that reality is far more participatory than we ever imagined. Consider the implications as you listen. Every time you open your eyes, every moment your consciousness engages with the world around you, you might be participating in a process far more mysterious and dynamic than simple passive observation. In the quantum realm, particles exist in what physicists describe as a superposition of states. Imagine trying to describe the location of a note in a symphony before it's played. Is it in the violin section, the piano, the clarinet, In a sense, it exists everywhere in the orchestra until the moment the conductor's baton falls and the music begins. This is how quantum particles behave before measurement. An electron doesn't have a definite position or momentum. Instead, it exists as a cloud of probability, a mathematical description that encompasses all possible states it could be found in. The wave function, as physicists call it, is like a map of potential realities. What makes this particularly fascinating is that these aren't just theoretical possibilities. The superposition is real and measurable. Particles in superposition can interfere with themselves, creating patterns that would be impossible if they existed in only one state at a time. It's as if the universe is allowing multiple contradictory realities to coexist until the moment of observation forces a choice. Scientists have pushed these boundaries to remarkable extremes. They've created superpositions with increasingly large objects, from individual atoms to molecules containing thousands of particles. Each experiment reveals that the quantum world's strange rules persist even as we approach the scale of everyday objects. But here's where the mystery deepens. The superposition doesn't gradually fade or slowly resolve into a definite state. Instead, it collapses instantaneously and completely the moment observation occurs. One instant, the particle is everywhere and nowhere. The next, it's precisely here, with specific properties that seem to crystallize out of pure possibility. This collapse appears to happen faster than light could travel across the quantum system. If you have a particle spread across a large region and you measure it at one location, the entire wave function throughout space instantaneously updates to reflect this new reality. It's as if information about the measurement somehow reaches every part of the system simultaneously, a phenomenon that remains mathematically consistent within quantum theory, even though it challenges classical intuition. Take a moment to breathe and consider what this might mean. The universe appears to be far more interconnected than classical physics suggested. Every observation, every interaction seems to ripple through the fabric of reality in ways that transcend our ordinary notions of space and time. The instantaneous nature of wave function collapse becomes even more puzzling when we consider quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, they form a single quantum system, where measuring one particle instantaneously affects the other, regardless of the distance between them. Imagine two coins that are somehow connected so that when one lands heads, the other must land tails, but neither has a predetermined outcome until the moment one is flipped. This is roughly analogous to quantum entanglement, except the coins might be separated by vast distances, even light years apart. When scientists measure the state of one entangled particle, its partner immediately takes on the corresponding complementary state. This correlation happens faster than light could travel between the particles, creating what appears to be an instantaneous connection across space. The measurement doesn't send a signal to the distant particle. Instead, the act of observation seems to collapse the shared wave function that encompasses both particles, determining their state simultaneously. This phenomenon has been verified in countless experiments, with entangled particles maintaining their mysterious connection across increasingly large distances. Scientists have demonstrated entanglement between particles separated by hundreds of kilometers using satellites to send entangled photons across continents and even into space. The implications stretch far beyond laboratory curiosities. Entanglement suggests that the universe is fundamentally non-local, meaning that distant parts of reality can be connected in ways that don't depend on signals traveling through space. This challenges our basic intuitions about cause and effect, locality, and the independence of distant objects. Some interpretations suggest that entanglement reveals something profound about the nature of space and time themselves. Perhaps what we experience as separate locations are actually different aspects of a more fundamental unity that exists beneath the surface of everyday reality. As you contemplate these ideas, you might notice how they echo certain experiences in your own life. Have you ever felt an inexplicable connection with someone far away, sensed when a loved one was in distress despite being separated by great distance? While these experiences aren't evidence of quantum effects in human consciousness, they do suggest that our intuitions about connection and separation might be more complex than classical physics would suggest. The question of what constitutes an observation in quantum mechanics has puzzled physicists since the theory's early days. Is consciousness required, or can any physical interaction serve as a measurement? This question strikes at the heart of understanding the relationship between mind and matter in the quantum world. Early interpretations, particularly those developed by the Copenhagen School of Quantum Mechanics, emphasized the role of measurement without clearly defining what distinguishes a measurement from any other interaction. This ambiguity led some physicists to suggest that consciousness itself might play a special role in wave function collapse. The consciousness-based interpretation proposed that quantum systems remain in superposition until observed by a conscious mind. In this view, the entire universe would exist in a vast superposition of all possible states until conscious observers evolved to collapse portions of it into definite realities. This idea captured the imagination of many people, extending far beyond the physics community. However, most physicists today favor explanations based on decoherence rather than consciousness. Decoherence theory shows how quantum systems lose their superposition properties through interaction with their environment, without requiring any special role for conscious observers. Every quantum system exists within an environment of other particles, fields, and forces. These environmental interactions constantly disturb the delicate superposition states, causing what appears to be wave function collapse. The environment acts like a continuous measuring device, constantly extracting information about the quantum system and destroying its quantum coherence. This process happens extraordinarily quickly for macroscopic objects. A dust particle in air loses its quantum coherence in less than a billionth of a second due to collisions with air molecules. Even in the vacuum of space, interactions with stray photons and particles ensure that large objects behave classically rather than quantum mechanically. Yet the fundamental mystery remains. Decoherence explains why macroscopic objects don't exhibit quantum behavior, but it doesn't fully resolve the measurement problem. The question of how and why definite outcomes emerge from quantum possibilities continues to challenge physicists and philosophers alike. Some interpretations avoid the problem altogether by proposing that wave function collapse never actually occurs. The many worlds interpretation, for example, suggests that all possible outcomes of quantum measurements happen simultaneously in parallel universes. In this view, observation doesn't collapse the wave function, but rather selects which branch of reality we experience. Other approaches propose that the wave function represents our knowledge about a system rather than the system's actual state. These epistemic interpretations treat quantum mechanics as a theory about information and prediction rather than a fundamental description of reality itself. As you consider these different possibilities, notice how each interpretation reflects different assumptions about the nature of reality and our place within it. The question of what constitutes observation touches on deep philosophical issues about the relationship between subjective experience and objective reality. Perhaps the most perplexing aspect of quantum measurement is how a theory that describes the microscopic world in terms of probabilities and possibilities somehow produces the definite, classical world we experience every day. This transition from quantum to classical behavior remains one of the deepest mysteries in physics. Quantum mechanics is incredibly successful at predicting the statistical outcomes of measurements on quantum systems. It can tell you the probability of finding a particle in a particular state, the likelihood of detecting a photon at a specific location, or the chances of measuring a particular value for a quantum property. But it cannot predict which specific outcome will occur in any individual measurement. This fundamental randomness appears to be built into the fabric of reality itself. Unlike classical systems, where randomness typically reflects our ignorance of the complete state of a system, quantum randomness seems irreducible. Even with complete knowledge of a quantum system before measurement, the best you can do is calculate probabilities. This probabilistic nature troubled many early physicists, including Einstein, who believed that a complete theory should be deterministic. His famous objection that God does not play dice with the universe reflected a deep philosophical commitment to the idea that physical events should have definite causes and predictable effects. But experiments have consistently supported the quantum view. Tests of Bell's inequalities, mathematical relationships that must hold if reality is both local and deterministic, have repeatedly shown violations that confirm the quantum mechanical predictions. These experiments demonstrate that the universe cannot be both local and deterministic in the classical sense. The randomness of quantum measurements raises profound questions about the nature of causality and free will. If fundamental physical events are truly random, what does this mean for the chain of cause and effect that seems to govern the macroscopic world? How do random quantum events give rise to the apparently deterministic behavior of classical objects? The answer lies partly in the law of large numbers. While individual quantum events are unpredictable, the statistical behavior of large collections of quantum systems becomes highly predictable. Just as you can't predict the outcome of a single coin flip, but can confidently predict that a million flips will yield approximately half heads and half tails, the aggregate behavior of quantum systems follows reliable statistical patterns. This statistical predictability allows the classical world to emerge from quantum foundations. The seemingly solid objects around you are composed of vast numbers of quantum particles whose individual behaviors are random, but whose collective behavior follows the deterministic laws of classical physics. Yet this explanation doesn't fully resolve the mystery of measurement. The transition from quantum possibilities to classical actualities still requires some mechanism that selects specific outcomes from the range of quantum possibilities. Whether this mechanism involves consciousness, environmental decoherence, or something else entirely remains an open question. As you reflect on these ideas, consider how they might relate to your own experience of choice and decision-making. In your daily life, you make countless decisions that seem to emerge from a space of open possibilities. While we don't yet understand how consciousness relates to quantum mechanics, the quantum world does offer a metaphor for understanding how definite choices might emerge from indefinite possibilities. One of the most mind-bending aspects of quantum observation involves the relationship between measurement and time. In the classical world, we assume that events happen in a definite sequence, with past events determining future ones. But quantum mechanics suggests that this linear view of causality might be incomplete. John Wheeler's delayed choice experiments demonstrated that decisions about how to observe a quantum system can be made after the system has already interacted with the experimental apparatus. In these experiments, the choice of measurement seems to affect how the system is described from a scientific standpoint, influencing the interpretation of its earlier behavior without implying that the literal past was changed. Consider a photon traveling through an interferometer, a device that splits the photon's path and then recombines it. If you decide to measure which path the photon took after it has already passed through the device, but before it reaches the final detector, the photon behaves as if it went through only one path. If you choose not to measure the path, the photon behaves as if it went through both paths simultaneously, creating an interference pattern. The striking aspect of these experiments is that the decision about whether to measure the path can be made by a random number generator at the last possible moment, after the photon has already traversed the interferometer. Yet this future decision seems to determine the photon's past behavior. This doesn't mean that the future literally rewrites the past, but rather that the properties we observe in quantum systems might not be fully determined until the complete measurement process is finished. The past, present, and future might be more interconnected in the quantum world than our everyday experience suggests. Recent experiments have pushed these ideas even further, demonstrating quantum effects that seem to involve correlations across time as well as space. These temporal correlations suggest that the quantum world operates according to a logic that transcends our ordinary understanding of temporal sequence. Some interpretations of quantum mechanics propose that time itself might be an emergent property rather than a fundamental aspect of reality. In this view, the flow of time and the sequence of cause and effect might arise from more fundamental quantum processes that don't respect our usual notions of temporal order. These ideas invite us to reconsider our understanding of memory, anticipation, and the experience of temporal flow. While consciousness almost certainly doesn't operate according to quantum mechanical principles in any direct sense, the quantum world does offer new metaphors for understanding how past, present, and future might be more intimately connected than classical physics suggested. As you listen, you might notice how your own consciousness seems to exist in a perpetual present moment that somehow contains echoes of the past and anticipations of the future. The quantum perspective suggests that this temporal complexity might reflect something fundamental about the nature of reality itself. Information plays a central role in quantum mechanics, yet the nature of quantum information differs fundamentally from classical information in ways that challenge our understanding of knowledge, communication, and reality itself. In the classical world, information can be copied freely. You can photocopy a document, save multiple copies of a file, or repeat a message without altering the original. But quantum information behaves differently. The no-cloning theorem proves that it's impossible to create perfect copies of unknown quantum states. This limitation isn't just a practical constraint, it's a fundamental feature of quantum mechanics that has profound implications for our understanding of information and reality. If quantum states could be freely copied, many of the strange features of quantum mechanics, including the uncertainty principle and the measurement problem, would disappear. The inability to clone quantum information is intimately connected to the measurement problem. When you measure a quantum system, you gain classical information about it, but this process necessarily disturbs the system, destroying some of its quantum properties. You can't extract complete information about a quantum state without fundamentally altering it. This creates a trade-off between knowledge and preservation. To learn about a quantum system, you must change it. To preserve its quantum properties, you must remain partially ignorant about its state. This trade-off suggests that information and reality are deeply linked in ways that classical physics didn't fully anticipate. Quantum entanglement adds another layer of complexity to quantum information. Entangled particles share quantum information in a way that seems to transcend spatial separation. When you measure one particle of an entangled pair, you instantly gain information about its partner, regardless of the distance between them. Yet this instantaneous correlation can't be used for faster-than-light communication. The results of quantum measurements are fundamentally random, so you can't encode a message in the outcome of measuring your particle. The correlation only becomes apparent when the measurement results from both particles are compared, which requires classical communication that respects the speed of light. This limitation points to a deep feature of quantum mechanics: the distinction between quantum and classical information. Quantum correlations can exist instantaneously across space, but extracting classical information from these correlations requires local measurements that introduce randomness. Some physicists have proposed that information, rather than matter or energy, might be the most fundamental constituent of reality. John Wheeler's "it from bit" hypothesis suggests that all physical entities are information theoretic in origin, emerging from the processing of binary choices and quantum measurements. In this view, the universe might be understood as a vast information processing system, where particles, forces, and fields are different aspects of underlying informational relationships. Observation and measurement become acts of information extraction that help define the reality we experience. As you contemplate these ideas, consider how they might relate to your own experience of learning and knowing. Every time you gain information about the world, you participate in a process that might be more fundamental than you realize. Your consciousness, with its ability to process and integrate information, might be engaging with the same deep principles that govern the quantum world. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. One of the most profound questions in quantum mechanics is how the definite, predictable world of classical physics emerges from the probabilistic, uncertain foundations of the quantum realm. This emergence isn't just a mathematical curiosity, but touches on fundamental questions about the nature of reality and our place within it. The transition from quantum to classical behavior doesn't happen at a sharp boundary. Instead, it's a gradual process governed by the size, complexity, and environmental interactions of quantum systems. Small, isolated systems can maintain their quantum properties for extended periods, while large, complex systems quickly lose their quantum coherence and begin behaving classically. Decoherence theory provides the most widely accepted explanation for this transition. As quantum systems interact with their environment, they become entangled with vast numbers of environmental degrees of freedom. This entanglement spreads the quantum information throughout the environment, making it practically impossible to access or reverse the quantum superposition. The result is that quantum systems appear to collapse into classical states, even though the underlying quantum information is simply dispersed rather than destroyed. From our perspective as macroscopic observers, the system behaves classically because we can't access the environmental information needed to reveal its quantum nature. This process happens extraordinarily quickly for everyday objects. A grain of sand loses its quantum coherence in a tiny fraction of a second due to interactions with air molecules, photons, and other environmental factors. Even in the near-perfect vacuum of space, stray particles and radiation ensure that macroscopic objects behave according to classical physics. Yet the boundary between quantum and classical behavior isn't fixed. Scientists have demonstrated quantum effects in increasingly large and complex systems, from individual molecules to collections of billions of atoms. These experiments push the limits of where quantum mechanics applies and reveal that the classical world emerges gradually rather than abruptly from quantum foundations. The emergence of classical reality also involves the appearance of definite properties from quantum indefiniteness. In the quantum world, particles don't have well-defined positions, velocities, or other properties until measured. Yet in the classical world, objects appear to have definite locations, speeds, and characteristics independent of observation. This transition involves what physicists call the appearance of classical correlations from quantum ones. As quantum systems decohere, their correlations with the environment create the appearance of classical properties. What we perceive as the definite location of an object is actually a complex pattern of correlations between the object and its environment. These correlations are so strong and stable that they create the illusion of objective, observer-independent properties. The tree outside your window appears to have a definite height, not because it possesses this property independently, but because its quantum state is so thoroughly correlated with its environment that measurements of its height yield consistent, predictable results. This perspective suggests that classical reality is not fundamental but emergent. The solid, definite world we experience arises from underlying quantum processes that are inherently probabilistic and relational. Properties exist not as intrinsic features of objects, but as stable patterns of correlation between systems and their environments. As you consider these ideas, notice how they might relate to your own experience of stability and change. Your sense of having a consistent identity over time might emerge from complex patterns of correlation between your consciousness, your body, and your environment. The apparent solidity of your experience might reflect the same principles that give rise to classical reality from quantum foundations. While mainstream physics generally avoids attributing special properties to consciousness in quantum mechanics, the relationship between awareness, observation, and reality remains one of the most intriguing aspects of quantum theory. This relationship raises profound questions about the nature of consciousness and its place in the physical universe. The measurement problem in quantum mechanics inevitably touches on questions about consciousness, because measurement seems to require something that can register and record information about quantum systems. While most physicists agree that consciousness is not necessary for wave function collapse, the question of what exactly constitutes a measurement remains unresolved. Some interpretations have suggested that consciousness plays a fundamental role in quantum mechanics. These approaches propose that quantum systems remain in superposition until observed by a conscious mind, making consciousness a necessary component for the transition from quantum possibilities to classical realities. However, This consciousness-based interpretation faces significant challenges. It requires explaining how consciousness differs from other physical processes in its ability to collapse wave functions. It also leads to puzzling questions about the quantum state of the universe before conscious beings evolved and about the level of consciousness required for measurement. Most physicists today favour explanations that don't require consciousness to play a special role. Decoherence theory shows how environmental interactions can cause the appearance of wave function collapse without invoking consciousness. Any sufficiently complex system that can record information about a quantum state can serve as a measuring device. Yet the question of consciousness and quantum mechanics hasn't disappeared entirely. Some researchers have explored whether quantum effects might play a role in brain function and consciousness itself. While the brain is generally too warm and noisy to maintain quantum coherence for significant periods, some theories propose that quantum processes might contribute to neural computation and conscious experience. These ideas remain highly speculative and controversial. The brain appears to operate primarily according to classical physics, with neural activity following predictable patterns that don't require quantum explanations. Most neuroscientists believe that consciousness emerges from classical information processing in neural networks. However, recent research has revealed quantum effects in some biological systems, including photosynthesis, bird navigation, and possibly even enzyme function. While these discoveries don't directly implicate quantum mechanics in consciousness, they do show that biological systems can harness quantum effects under certain conditions. The relationship between consciousness and quantum mechanics also raises philosophical questions about the nature of subjective experience. If quantum mechanics reveals that properties emerge from interactions rather than existing independently, what might this suggest about the nature of conscious experience itself? Some interpretations propose that consciousness, like other classical properties, might emerge from underlying quantum processes through decoherence and environmental interaction. In this view, subjective experience would be a macroscopic phenomenon that arises from microscopic quantum processes, similar to how classical objects emerge from quantum foundations. Others suggest that consciousness might involve different principles entirely, operating according to logic that transcends both classical and quantum physics. The hard problem of consciousness, explaining how subjective experience arises from physical processes, remains unresolved regardless of whether those processes are classical or quantum. As you reflect on your own conscious experience while listening to these ideas, notice how awareness itself seems to involve a kind of observation. Your consciousness appears to collapse the vast array of possible thoughts, sensations, and experiences into the present moment content of your awareness, giving shape to the specific experience you're having right now. While this parallel doesn't prove that consciousness operates according to quantum principles, it does suggest that the act of observation, whether in physics or in consciousness, involves a mysterious transition from possibility to actuality that we're still working to understand. As we venture deeper into the quantum mystery, something remarkable begins to emerge from all these strange phenomena. The observer effect, wave function collapse, quantum entanglement, the measurement problem, all of these seemingly separate puzzles start to weave together into a larger pattern that challenges our most basic assumptions about separateness and connection. In our everyday experience, objects appear to be distinct and independent. Your chair exists separately from your table. The moon follows its orbit regardless of what happens on Earth. Cause and effect flow in orderly sequences from past to future. But the quantum world whispers a different story entirely. Consider how quantum entanglement reveals that particles separated by vast distances can remain connected in ways that transcend space and time. When measurement occurs on one particle, its entangled partner responds in a way that reflects the shared quantum correlations between them, as if the concept of separation were somehow illusory at the deepest level of reality. This isn't just a curious laboratory effect, it points towards something profound about the interconnected nature of existence itself. The implications ripple outward in ways that touch every aspect of how we understand our place in the universe. If particles that have never directly interacted can become entangled through their shared history, what does this suggest about the web of connections that might exist throughout the cosmos? Every photon that reaches your eyes from a distant star carries with it a quantum history that connects you, however tenuously, to the nuclear furnace where that light was born. Some interpretations suggest that entanglement might be far more pervasive than we initially realized. Quantum field theory reveals that the vacuum of space itself seethes with virtual particle pairs constantly appearing and disappearing. These fleeting particles become entangled in the moment of their creation, creating a hidden network of correlations that spans the universe. This quantum foam, as physicists sometimes call it, means that even empty space isn't truly empty or disconnected. Every region of space maintains quantum correlations with every other region, creating an invisible web of relationship that underlies the apparent separateness of classical objects. The solid boundary between self and world, between here and there, begins to soften when viewed through the lens of quantum mechanics. Take a moment to sense your own place within this interconnected web. As you breathe, you're exchanging atoms with the atmosphere around you. Some of the carbon in your body was forged in stellar cores billions of years ago. The quantum fields that describe your electrons are the same fields that describe electrons throughout the universe. In the deepest sense, the quantum perspective suggests that separation might be a useful illusion rather than an absolute truth. This interconnectedness becomes even more intriguing when we consider the role that information plays in quantum mechanics. The measurement process isn't just about gaining knowledge about a quantum system, it's about the flow of information that seems to participate in creating the reality we observe. When a quantum measurement occurs, information flows from the quantum system to the measuring device, and ultimately to conscious observers. But this isn't passive information transfer, like reading words on a page. The act of information extraction appears to fundamentally alter the system being observed, suggesting a deep relationship between knowledge and reality. This relationship extends to the quantum no-cloning theorem, which proves that quantum information cannot be perfectly copied. Unlike classical information, which can be duplicated endlessly without loss, quantum information is unique and fragile. When you learn something about a quantum system through measurement, that information can never be perfectly replicated or restored. The impossibility of cloning quantum information has profound implications for understanding the nature of reality and identity. If quantum systems cannot be perfectly copied, then each quantum state is unique and irreplaceable. This uniqueness might extend upward through the layers of complexity that build from quantum foundations to create the classical world we experience. Consider what this might mean for your own existence. While you're primarily a classical system governed by everyday physics, you're built from quantum components that follow quantum rules. The quantum uniqueness principle suggests that your particular arrangement of matter and energy has never existed before and will never exist again. In a very real sense, you are irreplaceable, not just emotionally or socially, but physically and informationally. The flow of information in quantum systems also reveals something fascinating about the nature of time and causality. Information appears to flow both forward and backward in time in quantum mechanics, creating correlations that transcend our usual understanding of temporal sequence. Wheeler's delayed choice experiments demonstrate that future decisions can seem to influence past events, suggesting that the flow of information in quantum systems operates according to principles that don't map neatly onto our everyday sense of time. Some interpretations propose that information might be more fundamental than matter or energy. In this view, particles, fields, and forces emerge from underlying informational relationships rather than being basic building blocks of reality. The universe becomes a vast information processing system where consciousness, measurement, and physical events are different aspects of information flow. As you contemplate these ideas, notice how your own consciousness seems to exist at the intersection of information and experience. Your thoughts, memories, and perceptions involve the processing and integration of information in ways that create your subjective experience of being. While we don't yet understand how consciousness relates to quantum information processing, the quantum world does offer new metaphors for understanding how information and experience might be more intimately connected than classical physics suggested. One of the most delicate and beautiful aspects of quantum mechanics is the phenomenon of quantum coherence, the ability of quantum systems to maintain superposition states and exhibit wave-like interference effects. Coherence is what allows particles to exist in multiple states simultaneously and creates the interference patterns that reveal the quantum nature of reality. But coherence is extraordinarily fragile. The slightest interaction with the environment can destroy it, causing quantum systems to lose their wave-like properties and begin behaving classically. This fragility initially suggested that quantum effects would be irrelevant to the warm, noisy, complex world of biology and everyday life. However, recent discoveries have revealed that nature has found remarkable ways to protect and harness quantum coherence, even in complex biological systems. Photosynthesis, the process by which plants convert sunlight into chemical energy, appears to use quantum superposition to explore multiple pathways simultaneously, allowing energy to find the most efficient route through the molecular machinery of chloroplasts. Bird navigation might rely on quantum entanglement in specialized proteins in their visual systems, creating a kind of biological compass that can detect Earth's magnetic field through quantum mechanical effects. Even the sense of smell might involve quantum tunneling, where molecules create distinctive vibrational signatures that consciousness somehow translates into the rich tapestry of scent. These biological quantum effects don't persist for long, typically lasting only picoseconds or femtoseconds before environmental decoherence takes over. But nature appears to have evolved sophisticated mechanisms to create protected spaces where quantum coherence can survive just long enough to influence biological processes. The discovery of quantum effects in living systems raises fascinating questions about the relationship between life and quantum mechanics. Did evolution discover quantum mechanical principles and learn to harness them, or does the quantum nature of reality create the conditions necessary for life to emerge? Some researchers speculate that consciousness itself might involve quantum processes, though this remains highly controversial and unproven. What's less speculative is how these discoveries challenge the boundary between the quantum and classical worlds. If biological systems can maintain quantum coherence under certain conditions, perhaps the separation between quantum weirdness and everyday experience isn't as clear-cut as once thought. Consider your own experience of aliveness as you listen to these words. Your consciousness somehow integrates vast amounts of information into coherent experience. Your brain processes sensory input, memories, thoughts and emotions into the unified field of awareness that constitutes your present moment experience. While we don't yet understand how consciousness works, the quantum perspective offers new metaphors for understanding how coherent experience might emerge from the complex information processing that occurs in biological systems. Some interpretations suggest that consciousness itself might be understood as a kind of biological quantum coherence, a delicate state that emerges when neural information processing reaches sufficient complexity and integration. This remains purely speculative, but it offers an intriguing possibility for understanding how subjective experience might arise from objective physical processes. As our exploration of quantum mechanics deepens, we encounter a beautiful paradox. The more we learn about the quantum world, the more mysterious it becomes. Each answer reveals new questions. Each explanation opens new depths of wonder. This isn't a failure of scientific understanding, but rather a reflection of the inexhaustible richness of reality itself. The measurement problem, despite decades of research and countless experiments, remains as puzzling today as it was when quantum mechanics was first developed. We can predict quantum behavior with extraordinary precision, design technologies based on quantum principles, and manipulate quantum systems with increasing sophistication. Yet the fundamental question of how and why observation transforms quantum possibilities into classical actualities continues to elude complete understanding. This persistent mystery invites a kind of intellectual humility that's both challenging and liberating. In our culture, we often assume that scientific progress means replacing mystery with knowledge, uncertainty with certainty. But quantum mechanics suggests a different relationship between knowledge and mystery, where deeper understanding reveals deeper questions rather than eliminating them. The quantum world teaches us that reality is far stranger, more subtle, and more interconnected than our everyday experience suggests. It challenges us to expand our concepts of causality, locality, objectivity, and even existence itself. Yet it does so not by abandoning rational inquiry, but by pushing reason to its limits and revealing the boundaries of what can be known through any conceivable measurement or observation. This limitation isn't a defeat for science, but rather an invitation to approach reality with a sense of wonder and openness that complements rigorous investigation. The quantum world suggests that mystery isn't the enemy of knowledge, but rather its deepest source and most profound expression. As you sit with these ideas, notice how they might shift something in your own relationship to knowing and not knowing. Perhaps the areas of your life that feel most mysterious, most uncertain, most open to possibility are not problems to be solved, but invitations to participate more fully in the ongoing creation of reality. The quantum perspective suggests that uncertainty and possibility are not obstacles to understanding, but rather fundamental features of a universe that remains creative, responsive, and alive. In a world governed purely by classical determinism, everything would be predictable and fixed. But in a quantum universe, genuine novelty and creativity remain possible at the deepest level of physical reality. This openness to genuine possibility might extend beyond physics into every domain of experience. While we can't claim that consciousness operates according to quantum principles, the quantum world does offer a powerful metaphor for understanding how life might remain fundamentally open to new possibilities even within the constraints of natural law. Perhaps the most profound gift of quantum mechanics is not its technological applications or its successful predictions, but rather the way it serves as a mirror for examining the nature of consciousness and experience. The quantum world reveals patterns and principles that resonate with the deepest aspects of aware existence, offering new ways of understanding the mystery of subjective experience. The observer effect suggests that the act of observation plays a fundamental role in determining what is observed. While this doesn't mean that awareness directly alters physical reality, it does point toward a participatory relationship between attention and experience that transcends the classical subject-object divide. In your own life, you might notice how the quality of attention you bring to any experience shapes what you discover within that experience. When you observe your thoughts with gentle curiosity rather than reactive judgment, different thoughts arise. When you pay attention to your emotions with acceptance rather than resistance, they transform in the very process of being witnessed. This parallel between quantum observation and conscious awareness doesn't prove that they operate according to the same principles, but it does suggest that the act of observation, whether in physics or in consciousness, involves a mysterious alchemy, where possibility crystallizes into actuality through the process of being witnessed. The quantum principle of superposition offers another mirror for understanding consciousness. Just as quantum particles can exist in multiple states simultaneously before measurement, your consciousness seems to hold multiple possibilities, perspectives, and potentials in a kind of experiential superposition. Thoughts, emotions, and sensations arise and dissolve in the field of awareness, like quantum possibilities manifesting and disappearing in the vacuum of space. The collapse of quantum superposition into definite states parallels the way that conscious attention seems to collapse the vast field of potential experience into the specific content of each present moment. While this is metaphorical rather than literal, the parallel suggests that consciousness and quantum mechanics might both be expressions of deeper principles governing how possibility becomes actuality. Quantum entanglement offers perhaps the most intriguing parallel with conscious experience. Just as entangled particles remain connected across arbitrary distances, consciousness seems to transcend the boundaries of space and time in subtle ways. Your awareness can hold memories from the past, anticipations of the future, and immediate present moment sensations in a unified field of experience that defies simple, spatial, or temporal location. Some interpretations suggest that consciousness might involve a kind of temporal entanglement, where past, present, and future exist in superposition within awareness until the moment of experience collapses them into the linear flow of psychological time. This remains purely speculative, but it offers an intriguing way of understanding how consciousness seems to exist both within time and somehow outside of it. The quantum world also mirrors the paradoxical nature of self-awareness. Just as quantum systems are fundamentally altered by the act of measurement, consciousness seems to change in the very process of observing itself. When you try to observe your thoughts, the thoughts change. When you attempt to examine the nature of awareness itself, the act of examination becomes part of what's being examined. This self-referential quality of consciousness has puzzled philosophers and scientists for centuries. The quantum measurement problem offers a new context for understanding how observation and observed, knower and known might be more intimately connected than our usual subject-object thinking suggests. As you continue to explore these parallels, remember that they remain metaphorical rather than literal. Consciousness almost certainly doesn't operate according to quantum mechanical principles in any direct sense. The brain is too warm, too noisy, and too large to maintain quantum coherence for the periods that would be required for quantum effects to directly influence conscious experience, yet the metaphors remain powerful and illuminating. They suggest ways of understanding consciousness that transcend the limitations of both purely materialist and purely dualist approaches. Perhaps consciousness and quantum mechanics are both expressions of deeper principles that govern how reality emerges from the interplay of possibility and actuality, observer and observed, knowledge and mystery. As our journey through the quantum world draws toward its close, we find ourselves not with answers, but with a deeper appreciation for the questions themselves. The observer effect reveals that reality is not a fixed stage upon which consciousness acts, but rather an ongoing dance between awareness and possibility, measurement and mystery, knowledge and the unknowable. The quantum world teaches us that the universe is far more participatory, interconnected, and creative than classical physics suggested. Every observation, every interaction, every moment of awareness participates as in the ongoing creation of the reality we experience. This doesn't mean that awareness shapes physical outcomes, but rather that the boundary between observer and observed, between mind and matter, might be more fluid and mysterious than we previously imagined. In the quantum realm, nothing exists in isolation. Particles are defined by their relationships, properties emerge from interactions, and information flows in patterns that transcend our usual notions of space and time. This interconnectedness extends upward through every level of complexity, from quantum fields to atoms to molecules to cells to organisms to consciousness itself. The fragility of quantum coherence reminds us that the extraordinary is always present within the ordinary, but it requires specific conditions to be revealed. Just as quantum effects require isolation from environmental decoherence, perhaps the deepest insights about consciousness and reality require a kind of inner stillness that allows subtle patterns to emerge from the background noise of everyday experience. The measurement problem, with its suggestion that observation plays a fundamental role in determining what is observed, invites us to consider the quality of attention we bring to each moment of experience. While we can't control reality through observation alone, the quantum perspective suggests that the act of witnessing might be more creative and participatory than we typically assume. As you carry these ideas with you into your daily life, notice how they might subtly shift your relationship to the world around you. Perhaps the solid boundaries between self and environment, between inner and outer, between known and unknown, are not as fixed as they appear. Perhaps reality is more fluid, more responsive, more alive with possibility than our habits of perception typically allow us to notice. The quantum world doesn't provide easy answers about the nature of consciousness or reality. Instead, it opens spaces for wonder, for uncertainty, for the kind of not knowing that makes genuine discovery possible. In a universe governed by quantum principles, mystery isn't a problem to be solved, but rather the creative source from which new realities continuously emerge. Perhaps this is the deepest gift of quantum mechanics, not its technological applications or its predictive power, but its invitation to approach reality with a kind of openness and wonder that allows us to participate more fully in the ongoing creation of the world we inhabit. Every moment offers the possibility of collapse from potential to actual, from possibility to presence, from quantum uncertainty to lived experience. In the end, the observer effect reminds us that we are not separate from the universe we observe, but rather integral participants in its unfolding. Every breath, every thought, every moment of awareness is part of the vast dance through which reality creates itself. And in that dance, the boundaries between observer and observed, between consciousness and cosmos, between mystery and revelation, dissolve into something far more beautiful than either could be alone. Take a breath and let yourself rest in the wonder of it all. You're not merely a passive observer of reality, but an active participant in its creation. And in this moment, as you listen to these words, as awareness meets experience, something new is being born that has never existed before and will never exist again. The quantum paradox of observation continues to unfold, not just in laboratories and equations, but in the living laboratory of consciousness itself, where every moment offers the possibility of discovering something new about the nature of what it means to be aware, to be alive, to be part of the magnificent mystery we call existence. If you found yourself drawn into the mysterious relationship between consciousness and reality, you might enjoy exploring how these same quantum principles appear when we examine the nature of belief itself. I invite you to discover quantum reality reacts when you stop believing your own thoughts, where we'll explore how the act of questioning our most basic assumptions about ourselves and the world might open doorways to experiences that are just as strange and wonderful as anything we've encountered in the quantum realm. The quantum observer effect has traditionally been understood as a laboratory phenomenon, something that happens to particles under highly controlled conditions, isolated from the messy complexity of the everyday world. But what if this perspective is too narrow? What if the principles that govern quantum observation extend into realms we've barely begun to explore? Recent research in quantum biology has revealed that nature herself has been harnessing quantum effects for billions of years, long before humans built their first particle accelerators. In the delicate machinery of photosynthesis, energy from sunlight appears to explore multiple pathways simultaneously through quantum superposition, finding the most efficient route to chemical conversion with an effectiveness that surpasses our most sophisticated solar panels. This isn't speculation or wishful thinking. Scientists have measured quantum coherence in the light harvesting complexes of green plants, algae, and certain bacteria. These biological systems maintain quantum superposition for hundreds of femtoseconds, long enough for quantum effects to influence the outcome of energy transfer. It's as if evolution discovered quantum mechanics millions of years before physicists did. Consider the European robin, that small bird whose navigation abilities have puzzled scientists for decades. Recent research suggests that these birds might literally see magnetic fields through quantum entanglement occurring in specialized proteins in their eyes. Pairs of electrons become entangled when light hits these proteins, creating a kind of biological compass that allows the bird to perceive Earth's magnetic field as visual patterns overlaid on their normal vision. The implications stretch far beyond biology textbooks. If quantum effects can persist in the warm, noisy environment of living cells, then the boundary between the quantum and classical worlds might be far more permeable than we once believed. Perhaps the observer effect extends into territories we've never thought to explore. As you contemplate these discoveries, notice how they might shift your understanding of the natural world around you. That tree outside your window might be engaged in quantum information processing with every photon it absorbs. The birds singing in the morning might be navigating through quantum correlations that span continents. You exist within a world where quantum mystery operates not just in sterile laboratories, but in every leaf, every cell, every breath of life. This brings us to one of the most intriguing frontiers in consciousness research: the question of whether awareness itself might involve processes that parallel quantum measurement. While we must be careful not to make claims beyond what evidence supports, the parallels are striking enough to warrant careful consideration. When you pay attention to your breathing, something remarkable happens. The simple act of observing your breath changes it. The rhythm shifts, the depth alters, the quality of each inhalation and exhalation transforms under the gentle pressure of awareness. This doesn't imply a quantum mechanism is operating, but it does illustrate how observation in consciousness can reshape the experience being observed. This observer effect in consciousness extends far beyond breathing. When you watch your thoughts without judgment, they begin to change. Anxious mental patterns that seem solid and overwhelming often dissolve under sustained, gentle observation. Emotions that felt permanent and fixed reveal themselves to be fluid and responsive to the quality of attention they receive. Some interpretations suggest that consciousness might operate according to principles that loosely resemble quantum mechanics, though this remains unproven and highly speculative. The idea is not that your thoughts directly influence quantum systems, but rather that awareness itself might involve the same fundamental relationship between observation and experience that we see in quantum mechanics. Consider the phenomenon of attention itself. In any moment, your consciousness seems to exist in a superposition of potential experiences. You could focus on the sounds around you, the sensations in your body, the flow of thoughts through your mind, or the quality of emotion present in this moment, until attention collapses this experiential superposition into a specific focus. All possibilities seem to coexist in the field of awareness. The parallel isn't perfect, and we must be clear that this is metaphorical rather than literal. Consciousness doesn't follow quantum mechanical equations, and your thoughts don't directly collapse wave functions in the physical world. But the structural similarity is intriguing enough to suggest that both quantum mechanics and consciousness might be expressions of deeper principles governing how possibility becomes actuality. Take a moment to experiment with this idea. As you listen, let your attention rest gently on the quality of awareness itself. Notice how the act of observing consciousness seems to change what's being observed. The observer and the observed begin to merge in a way that echoes the fundamental mystery of quantum measurement. In quantum field theory, particles are understood as excitations in underlying fields that permeate all of space: the electron field, the photon field, the quark field. These invisible substrates give rise to the particles we observe when sufficient energy creates a localized disturbance in the field. Empty space isn't truly empty, but filled with fluctuating quantum fields, a seething sea of virtual particles constantly appearing and disappearing. This perspective offers a profound metaphor for understanding consciousness and experience. What if awareness itself is like a field, an invisible substrate from which thoughts, emotions, sensations, and perceptions arise as temporary excitations. In this view, consciousness wouldn't be produced by the brain, but would be more like a fundamental aspect of reality that the brain learns to access and modulate. Some interpretations in consciousness studies suggest that individual minds might be like localized disturbances in a larger field of awareness, similar to how particles are excitations in quantum fields. This remains entirely speculative and not supported by current scientific evidence, but it offers an intriguing way of understanding the apparent continuity of consciousness despite the constant flux of mental content. Consider your own experience of thoughts arising and dissolving in awareness. Where do thoughts come from? They don't seem to be manufactured by some internal thought production facility. Instead, they appear spontaneously in the field of consciousness, persist for a time, and then fade away. The process resembles the way quantum particles emerge from and return to the vacuum of space. This field perspective might also help explain some of the more mysterious aspects of conscious experience, such as intuition, creativity, and the sense of connection that can arise between people in deep communication. If consciousness operates according to principles that parallel quantum field dynamics, then the boundaries between individual minds might be more fluid than our everyday experience suggests. Again, this is speculative territory where we must tread carefully. There's no scientific evidence that consciousness literally operates as a quantum field, and we must avoid claims that go beyond what can be reasonably supported. But as a metaphor for understanding the nature of awareness, the quantum field perspective offers rich possibilities for exploration. As you sit with these ideas, you might notice the field-like quality of your own awareness. Thoughts arise within consciousness like waves on the surface of the ocean, but the ocean itself remains essentially unchanged. The field of awareness seems to provide the space within which all experience occurs, yet it remains mysteriously distinct from any particular experience that arises within it. Quantum entanglement reveals that separated particles can maintain instantaneous correlations across arbitrary distances, suggesting that the universe is far more interconnected than classical physics assumed. This phenomenon of non-local correlation offers another compelling metaphor for understanding certain aspects of conscious experience that have long puzzled philosophers and scientists. Have you ever had the experience of thinking about someone you haven't spoken to in years, only to receive an unexpected call from them later that day? Or felt a sudden shift in mood that seemed to come from nowhere, later discovering that a close friend was going through a difficult time at exactly that moment? While these experiences don't constitute evidence of any literal physical entanglement between minds, they do suggest that consciousness might be more interconnected than our usual sense of individual separation suggests. Some researchers have explored whether groups of people might exhibit correlations that parallel quantum entanglement, though this remains highly controversial and unproven. The idea is not that human consciousness operates according to quantum mechanics, but rather that the same principles of interconnectedness that govern an entangled particles might serve as metaphors for certain aspects of conscious experience. Studies of meditation groups have occasionally reported correlations between individual practitioners that seem to exceed what chance would predict. Though these findings remain preliminary and disputed, some interpretations suggest that when people enter states of deep meditative absorption together, their individual consciousness might become synchronized in ways that feel interconnected, creating shared experiences or unified states of awareness. The Global Consciousness Project, which monitors random number generators around the world for signs of correlation, during major global events, has reported statistical anomalies that some interpret as possible indicators of collective consciousness effects. However, these findings remain controversial, with no scientific consensus about their significance or meaning. What's less controversial is the subjective experience of connection that many people report during deep meditation, meaningful conversation, or shared creative activities. These experiences of expanded awareness and dissolved boundaries don't require quantum explanations, but they do suggest that consciousness might be more fundamentally relational than our individual-focused culture typically recognizes. Consider your own experience of connection with others. In moments of deep empathy or understanding, the sense of separation between self and other can become remarkably fluid. You might find yourself knowing what someone is feeling without them expressing it explicitly, or experiencing a kind of shared awareness that transcends ordinary communication. While we must be careful not to attribute these experiences to literal quantum effects, the parallel with entanglement offers a useful metaphor for understanding how consciousness might transcend the boundaries of individual identity under certain conditions. Perhaps the observer effect in consciousness extends beyond individual observation to include shared or collective forms of awareness. As you reflect on your own experiences of connection and separation, notice how the quality of attention you bring to relationships affects the sense of boundary between self and other. Deep present attention seems to dissolve barriers, while distracted or judgmental attention reinforces separation. This suggests that the observer effect in consciousness might be fundamentally relational, emerging from the quality of awareness shared between conscious beings. One of the most practical applications of understanding the observer effect in consciousness involves the stories we tell ourselves about who we are and what's possible in our lives. These narratives, like quantum systems before measurement, often exist in a kind of superposition of possibilities until the moment we observe them with clear present awareness. Consider a persistent belief about yourself that limits your sense of what's possible. Perhaps you've always thought of yourself as someone who's not creative, not good with numbers, or not capable of deep relationships. These self-concepts often feel as solid and unchangeable as physical objects, but the observer effect in consciousness suggests they might be far more fluid than they appear. When you observe a limiting belief with the same quality of gentle, sustained attention that collapses quantum superpositions, something remarkable often happens. The belief begins to reveal itself as a construction rather than a fact, a pattern of thought rather than an immutable truth about reality. This isn't positive thinking or self-deception, but rather the natural result of seeing clearly what's actually present in consciousness. The stories we tell ourselves about past events operate according to similar principles. Memory isn't a passive recording, but an active reconstruction that changes each time we access it. When you recall a past experience with different quality of attention, with compassion instead of self-criticism, or curiosity instead of defensiveness, the memory itself begins to shift and transform. This doesn't mean that past events didn't happen or that facts are merely subjective. Rather, it suggests that the meaning we derive from experience, the way past events influence present possibilities, remains remarkably open to transformation through the quality of awareness we bring to them. Some interpretations in psychology and consciousness studies suggest that traumatic memories might exist in a kind of superposition until they're observed with sufficient safety and support to allow integration. The therapeutic process involves creating conditions where painful experiences can be witnessed without triggering overwhelming activation. allowing natural healing processes to unfold. This perspective offers a hopeful view of personal transformation. If the observer effect applies to consciousness as well as quantum systems, then patterns that seem fixed and unchangeable might actually be responsive to the quality of attention we bring to them. Change becomes possible not through force or effort, but through the patient application of clear, compassionate awareness. Take a moment to consider an area of your life where you feel stuck or limited. Instead of trying to change anything, simply observe what's actually present with gentle curiosity. Notice how the quality of observation itself begins to shift something in your experience of the situation, even if the external circumstances remain unchanged. The quantum world reveals that the act of observation is never neutral or passive, but always participatory and creative. This principle extends into every moment of daily life, where the quality of attention you bring to each experience helps determine what you discover within that experience. When you approach a conversation with genuine curiosity rather than the need to be right, different possibilities emerge from the interaction. When you observe your emotions with acceptance rather than resistance, they reveal subtleties and nuances that weren't apparent before. When you pay attention to the natural world with wonder rather than distraction, it responds with beauty and mystery that enrich your sense of connection to life itself. This participatory relationship between observer and observed operates across every scale of experience, from the most intimate moments of self-awareness to the broadest encounters with the natural and social world. The observer effect in consciousness suggests that reality is far more responsive and alive than our habits of perception typically allow us to notice. Consider how the quality of attention you bring to simple activities transforms those activities. Walking meditation, where you pay careful attention to the sensations of each step, reveals that walking is not just a means of transportation but a rich sensory experience, full of subtle variations and discoveries. Mindful eating transforms a meal from mere fuel consumption into an exploration of taste, texture, temperature, and the miracle of nourishment itself. Even routine activities like washing dishes or folding laundry become opportunities for practicing the observer effect in consciousness. When you bring full attention to these simple tasks, they often reveal unexpected dimensions of satisfaction and presence that weren't available when they were performed automatically or with resistance. The key insight is that nothing needs to change externally for your experience to transform dramatically. The transformation happens through the quality of awareness you bring to whatever is already present. This is both the subtlety and the power of the observer effect in consciousness. It works with what's already here rather than requiring different circumstances. Some meditation traditions suggest that the ultimate realization involves recognizing that ordinary experience, when observed with sufficient clarity and presence, reveals itself to be extraordinary. The observer effect in consciousness doesn't require special states or mystical experiences, but rather the willingness to see clearly what's always been present. As you go through your day, you might experiment with bringing the quality of attention that a quantum physicist brings to their experiments. Approach each interaction, each sensation, each moment of awareness as an opportunity to discover something new about the nature of reality and your place within it. Perhaps the most profound implication of the observer effect, both in quantum mechanics and in consciousness, is the suggestion that the universe might be understood as a vast system of observation observing itself. From this perspective, every act of measurement in physics and every moment of awareness in consciousness participates in the universe's ongoing process of self-discovery. Carl Sagan captured something essential when he observed that we are a way for the cosmos to know itself. Through human consciousness, the universe has evolved the capacity for self-reflection, for questioning its own nature, for marveling at its own complexity and beauty. Every moment of awareness becomes a kind of cosmic measurement, where the universe observes itself through billions of conscious beings. This perspective doesn't require any mystical or supernatural beliefs, but emerges naturally from considering the observer effect across all scales of reality. If observation plays a fundamental role in determining what becomes actual versus what remains potential, then consciousness represents the universe's most sophisticated means of exploring and experiencing itself, rather than implying any direct control over physical outcomes. The development of self-aware beings through evolution might be understood as the universe's way of developing increasingly sophisticated observation capabilities. From simple sensory awareness in early life forms to the complex self-reflection possible in human consciousness, evolution has created ever more nuanced ways for reality to observe and know itself. Some interpretations in cosmology and consciousness studies suggest that this process of cosmic self-observation might be fundamental to the universe's development rather than merely an accidental byproduct of complexity. This remains entirely speculative, but it offers a profound context for understanding the significance of conscious experience within the larger story of cosmic evolution. Individual moments of awareness from this perspective become participatory acts in the universe's ongoing self-creation. When you observe your thoughts with clarity, experience beauty in nature, or recognize the profound mystery of your own existence, you're participating in the cosmos coming to know itself through your particular form of consciousness. This doesn't make human beings the center of the universe, or suggest that consciousness is the only important aspect of reality. Rather, it places conscious experience within the larger context of universal evolution, where the development of observation and awareness represents one of the most remarkable achievements of cosmic complexity. Take a breath and consider the extraordinary fact of your own awareness. In this moment, billions of years of cosmic evolution have culminated in your capacity to contemplate the nature of reality itself. Through your consciousness, the universe observes itself, questions itself, and marvels at its own mystery. One of the most puzzling aspects of the observer effect in both quantum mechanics and consciousness is what philosophers call the infinite regression problem. If observation changes what's being observed, what observes the observer? And what observes the observer of the observer? This question points toward one of the deepest mysteries in both physics and consciousness studies. In quantum mechanics, this puzzle led to various interpretations about what constitutes a measurement and where the chain of observation ultimately terminates. Does it require a conscious observer, or can any sufficiently complex system serve as a measuring device? The question remains unresolved, pointing toward fundamental limits in our understanding of the relationship between observation and reality. In consciousness studies, the same puzzle appears as the hard problem of consciousness. How does subjective experience arise from objective physical processes? When you observe your thoughts, who or what is doing the observing? The observer seems to be both part of consciousness and somehow distinct from it, creating a paradox that has challenged philosophers and scientists for centuries. Some interpretations suggest that this infinite regression might point towards something fundamental about the nature of awareness itself. Perhaps consciousness is not produced by observation, but is rather the field within which observation occurs. In this view, awareness wouldn't be something that emerges from complexity, but would be a basic feature of reality, like space or time. This perspective finds echoes in certain meditation traditions that distinguish between the contents of consciousness and consciousness itself. Thoughts, emotions, sensations, and perceptions arise and dissolve within awareness, but awareness itself seems to remain constant and unchanging. The observer effect in consciousness might reveal not just how observation changes experience, but how experience arises within an unchanging field of awareness. Other approaches suggest that the infinite regression problem dissolves when we recognize that observation is always relational rather than absolute. There's no ultimate observer standing outside the system, but rather a web of relationships where each element serves as both observer and observed, depending on the context. Reality becomes participatory all the way down, with no need for a final foundation. This relational view finds support in quantum mechanics, where particles are increasingly understood as relationships rather than objects, and in systems theory, where complex behaviours emerge from the interactions between components rather than from any individual element. Perhaps consciousness operates according to similar principles, emerging from the relationships between different aspects of experience rather than from any central observer. As you contemplate these possibilities, notice how the very act of trying to observe consciousness creates the paradox. The harder you look for the observer, the more elusive it becomes. Yet something is obviously present that makes observation possible. This mystery points toward the fundamental nature of awareness itself, which seems to be both intimate and immediate, and yet ultimately incomprehensible. The infinite regression of observation might be less a problem to solve than a pointer toward the mystery that lies at the heart of both consciousness and quantum mechanics. Both domains reveal that the relationship between observer and observed is far more subtle and mysterious than our everyday thinking typically assumes. The observer effect reveals that measurement doesn't simply reveal pre-existing properties, but participates in shaping the reality that gets measured. This principle extends into the realm of meaning and significance, where the quality of attention we bring to experience helps determine what meaning emerges from that experience. Consider how the same event can have completely different meanings depending on the context and quality of awareness from which it's observed. A challenging conversation might be experienced as a threat to be defended against or as an opportunity for deeper understanding, depending on the mindset and attention brought to the interaction. The observer effect in consciousness suggests that meaning isn't simply discovered, but is co-created through the act of observation itself. This participatory nature of meaning has profound implications for how we understand truth, knowledge, and reality. While there are certainly objective aspects of existence that remain consistent regardless of observation, the significance and meaning of those facts emerge through the interaction between consciousness and experience. Scientific observation operates according to similar principles. While experiments reveal objective features of reality, the questions scientists choose to ask, the methods they use to investigate, and the conceptual frameworks they bring to their research all influence what aspects of reality become visible and meaningful. The observer effect in science isn't just about measurement disturbing quantum systems, but about how scientific consciousness participates in revealing certain aspects of reality while leaving others unexplored. Some interpretations in philosophy of science suggest that All knowledge emerges from this participatory relationship between consciousness and reality. Facts don't exist in isolation, but always within contexts of meaning that are shaped by the questions we ask and the methods we use to investigate. This doesn't make knowledge purely subjective, but recognizes that objectivity emerges from the careful application of intersubjective methods of observation and verification. In personal experience, this principle reveals why the same life circumstances can feel either meaningful and rich or empty and depressing, depending on the quality of attention brought to them. Meaning isn't something that exists independently, waiting to be discovered, but emerges from the conscious engagement with experience. This participatory nature of meaning offers tremendous hope for personal transformation. If meaning emerges from the interaction between consciousness and experience, then it remains possible to discover new significance and purpose in any situation through the application of different qualities of attention and awareness. Take a moment to consider an aspect of your life that currently feels meaningless or unsatisfying. Instead of trying to change the external circumstances, experiment with bringing a different quality of attention to the situation. Notice how meaning begins to emerge not from the circumstances themselves, but from the consciousness that engages with them. Quantum mechanics reveals that uncertainty isn't just a limitation of measurement, but a fundamental feature of reality itself. The uncertainty principle demonstrates that certain properties of quantum systems cannot be simultaneously determined with perfect precision, not due to inadequate measurement techniques, but because the properties themselves don't have definite values until measured. This principle offers a profound metaphor for understanding the role of uncertainty in conscious experience. Rather than being an obstacle to knowledge or happiness, uncertainty might be the creative space within which new possibilities emerge. Just as quantum uncertainty allows for the creativity and novelty we see throughout the natural world, psychological uncertainty might be essential for growth, learning, and transformation. Consider how the most meaningful experiences in life often arise from periods of uncertainty and not knowing. Falling in love involves embracing the uncertainty of how another person might respond. Creative breakthroughs emerge from periods of confusion and exploration where the outcome is unknown. Personal growth requires releasing fixed ideas about who you are and opening to new possibilities for becoming. Some interpretations in psychology and consciousness studies suggest that the capacity to tolerate uncertainty might be one of the most important skills for human flourishing. Rather than seeking to eliminate uncertainty through control or rigid thinking, wisdom might involve learning to dance with uncertainty as a creative partner, rather than viewing it as a threat. The observer effect in consciousness reveals that many of the certainties we cling to are actually constructions of thought rather than immutable truths about reality. When observed with clear awareness, beliefs about yourself, other people, and life itself often reveal themselves to be far more fluid and changeable than they initially appeared. This doesn't lead to relativism or the idea that all perspectives are equally valid, but rather to a more nuanced understanding of the relationship between knowledge and uncertainty. Certainty and uncertainty can coexist, with firm knowledge in some domains, allowing for greater openness and flexibility in others. The quantum world teaches us that reality itself dances between definite and indefinite, between determined and undetermined, between known and unknowable. This cosmic uncertainty principle might extend into consciousness, where the most profound insights often arise from the willingness to rest in not knowing while remaining open to what might emerge. As you sit with these ideas, notice your own relationship to certainty and uncertainty. Do you try to eliminate uncertainty through thinking and planning, or can you find a quality of awareness that remains stable and present even in the midst of not knowing? The observer effect in consciousness suggests that peace and wisdom might emerge not from achieving certainty, but from developing the capacity to observe uncertainty with clarity and acceptance. Every act of observation, whether in quantum mechanics or consciousness, creates ripple effects that extend far beyond the immediate moment of measurement. In quantum systems, the act of observation can influence not only the measured system, but also other systems with which it has interacted, creating cascading effects that propagate through networks of quantum correlation. In consciousness, the observer effect operates similarly. When you observe a pattern of thought or emotion with clear awareness, the effects often extend beyond that particular mental content to influence other aspects of your experience. Observing anger with compassion might transform not only the anger itself, but also your relationship to other challenging emotions. Recognizing a limiting belief about yourself might open new possibilities in areas of life that seem completely unrelated. These ripple effects help explain why small shifts in awareness can sometimes lead to dramatic changes in experience. Just as quantum measurements can trigger subtle chains of influence in correlated systems, moments of clear seeing in consciousness can catalyze transformations that propagate through your entire sense of self and relationship to life. Some meditation traditions speak of this as the power of mindfulness to transform not only individual experience, but also the quality of relationships and interactions with others. When you observe your reactions with awareness, rather than unconsciously acting them out, it creates space for more skillful responses that benefit both yourself and others. The observer effect in consciousness becomes a gift you offer to the world through the quality of presence you bring to each moment. Research in fields like family systems therapy and organizational psychology has documented similar ripple effects in social systems. When one person in a family or workplace begins to respond differently to familiar patterns, it often catalyzes changes throughout the entire system, even when other people aren't directly trying to change their behavior. These ripple effects also appear in neuroscience research on meditation and contemplative practices. Studies suggest that sustained attention practices can influence not only the specific neural networks involved in attention, but also networks involved in emotional regulation, self-awareness, and empathy. The observer effect in the brain seems to propagate through interconnected systems in ways that enhance overall well-being and function. The interconnected nature of these ripple effects points toward a more systemic understanding of both quantum mechanics and consciousness. Rather than viewing observation as an isolated event that affects only the immediate target of attention, we begin to see it as part of larger networks of relationship and influence that extend throughout the fabric of reality. Consider how your own moments of clear seeing and awareness might be creating ripple effects that extend far beyond your immediate experience. The quality of attention you bring to this moment influences not only your understanding of these ideas, but also your interactions with others, your relationship to yourself, and your participation in the larger web of consciousness and relationship that connects all life. As we reach the final movements of our exploration, we find ourselves at the threshold of perhaps the most intriguing question of all: what happens when consciousness itself becomes the object of quantum-inspired investigation? While we've journeyed through the landscapes of observation and measurement, of superposition and entanglement, there remains one more territory to explore: the possibility that awareness itself might operate according to principles that echo, however faintly, the strange logic of the quantum world. This isn't to suggest that your thoughts directly manipulate wave functions, or that meditation can influence particle behavior. Rather, it's to consider whether the same fundamental relationship between observer and observed that governs quantum mechanics might also illuminate something profound about the nature of conscious experience itself. Recent research in neuroscience has begun to reveal that consciousness appears to emerge from what scientists call integrated information, complex patterns of neural activity that somehow give rise to the unified field of awareness that constitutes your subjective experience. While this process almost certainly operates according to classical physics rather than quantum mechanics, the parallels are striking enough to warrant careful consideration. Consider the phenomenon of attention itself. In any given moment, your brain processes vast amounts of information: sensory input from your environment, memories from your past, anticipations of the future, bodily sensations, emotional tones. Yet somehow, consciousness selects and integrates only a tiny fraction of this information into the coherent experience of the present moment. This selection process bears a remarkable resemblance to quantum measurement. Just as quantum observation collapses a superposition of possibilities into a single, definite outcome, attention seems to collapse the vast superposition of potential experiences into the specific content of awareness. The parallel isn't literal, but it's suggestive enough to offer new ways of understanding how consciousness might work. Some interpretations in consciousness studies, though this remains highly speculative and unproven, suggest that the brain might operate as a kind of biological analogue to certain quantum logic structures, using principles of parallel processing to integrate information efficiently. While the brain is generally too warm and noisy to maintain quantum coherence for significant periods, some researchers have proposed that certain neural structures might create protected spaces where subtle quantum influences could play a supportive role in information processing. This remains entirely theoretical, with no scientific consensus supporting such ideas. Most neuroscientists believe that classical physics is sufficient to explain brain function and consciousness. Yet the question persists: might there be subtle quantum influences in neural processing that we haven't yet learned to detect or understand? As you consider these possibilities, notice how the very act of contemplating consciousness seems to change your experience of being conscious. The observer effect in awareness reveals itself not through exotic quantum phenomena, but through the simple recognition that attention transforms whatever it touches, including attention itself. Perhaps the most practical insight emerging from our exploration involves the recognition that every moment of experience occurs within what we might call the theatre of presence, a space where possibilities continuously crystallize into actualities through the mysterious alchemy of awareness meeting reality. In this theatre, you are simultaneously the observer, the observed, and the observing itself. Unlike quantum systems, where the distinction between observer and observed can be maintained with some clarity, in consciousness, these roles blur and merge in ways that reveal the participatory nature of experience itself. Consider this very moment as you listen to these words. Your awareness is simultaneously observing the content of what's being said, the quality of your attention, the sensations in your body, the emotional tone of the moment, and countless other aspects of experience. Yet somehow, All of these observations are unified into the single, coherent field of present moment awareness. This unification process shares certain structural similarities with quantum measurement, though again, this is metaphorical rather than literal. Just as quantum measurement seems to collapse multiple possibilities into a single outcome, conscious attention seems to integrate multiple streams of information into unified experience. The difference is that consciousness appears to maintain awareness of this integration process in a way that quantum systems cannot. Some meditation traditions describe this as the recognition of awareness itself, the discovery that consciousness is not produced by experience, but is rather the space within which all experience arises. From this perspective, thoughts, emotions, sensations, and perceptions are like waves on the ocean of awareness, arising and dissolving without disturbing the fundamental nature of consciousness itself. This oceanic metaphor offers another parallel with quantum field theory, where particles are understood as temporary excitations in underlying fields that permeate all of space. Perhaps individual thoughts and experiences are like temporary excitations in the field of consciousness, arising from and returning to a deeper substrate of pure awareness. While this remains a metaphorical rather than scientific description, it offers a framework for understanding some of the more mysterious aspects of conscious experience, such as the sense of continuity that persists despite the constant flux of mental content, or the capacity for awareness to observe itself without fragmenting into infinite regression. Take a moment to rest in this theatre of presence. Notice how awareness seems to provide the space within which all experience occurs, yet it remains mysteriously distinct from any particular experience that arises within it. This recognition doesn't require special states or unusual experiences. It's available in the simple acknowledgement of the aware space that's reading these words right now. As our journey through the quantum paradox draws toward its natural conclusion, we encounter perhaps the most profound implication of all: the gradual dissolution of the apparent separation between observer and observed, between consciousness and cosmos, between the quantum world and the world of everyday experience. Throughout our exploration, we've seen how quantum mechanics challenges our classical assumptions about locality, causality, and objective reality. We've discovered that observation plays a fundamental role in determining what becomes actual versus what remains potential. We've contemplated how consciousness itself might operate according to principles that parallel, however distantly, the strange logic of quantum measurement. But perhaps the deepest insight isn't about particles or wave functions or measurement problems. Perhaps it's about the recognition that the boundary between inner and outer, between subjective and objective, between mind and matter, is far more fluid and mysterious than our everyday thinking typically acknowledges. The quantum world reveals that reality is fundamentally relational rather than consisting of independent objects with fixed properties. Particles exist as relationships, properties emerge from interactions, and information flows in patterns that transcend our usual notions of space and time. This relational view of reality finds echoes in certain approaches to understanding consciousness, where experience is seen as emerging from relationships rather than being produced by any single component. Some interpretations, though this remains entirely speculative, suggest that consciousness and quantum mechanics might both be expressions of deeper principles governing how possibility becomes actuality, how potential crystallizes into experience, how the observer and observed participate together in the ongoing creation of reality. This participatory view doesn't mean that consciousness controls reality through direct influence, but rather that the quality of awareness we bring to each moment influences what we discover within that moment. The observer effect extends beyond physics laboratories into every domain of experience, where the act of witnessing, whether gentle or harsh, curious or judgmental, open or closed, helps determine what emerges from the infinite field of potential. Consider how this recognition might shift your relationship to the world around you. If observation is always participatory rather than passive, then every moment offers the opportunity to contribute something valuable to the ongoing creation of reality. Not through force or manipulation, but through the simple gift of clear, compassionate awareness. The quantum paradox ultimately returns us to the mystery of existence itself, the inexplicable fact that there is something rather than nothing, that awareness has somehow emerged from the cosmic dance of matter and energy, that the universe has evolved the capacity to observe and know itself through conscious beings like ourselves. This mystery doesn't diminish with scientific understanding, but deepens and enriches with every new discovery. The more we learn about the quantum foundations of reality, the more wondrous and mysterious existence becomes. Knowledge and wonder grow together rather than being in opposition, each discovery opening new depths of appreciation for the extraordinary nature of ordinary existence. As you carry these insights with you beyond this exploration, remember that you're not merely a passive observer of the quantum universe, but an active participant in its ongoing self-discovery. Every moment of clear seeing, every act of compassionate awareness, every recognition of the interconnected nature of existence contributes to the universe's ancient project of coming to know itself. In the end, the quantum paradox of observation teaches us that reality is far more alive, responsive, and mysterious than classical physics ever suggested. We live within a cosmos that remains creative at every level, where genuine novelty continues to emerge through the eternal dance between possibility and actuality, between observer and observed, between consciousness and the infinite mystery from which it arises. Take a final breath with these ideas. Let them settle into your awareness, not as conclusions to be grasped, but as invitations to remain open to the ongoing revelation of what it means to be conscious, to be alive, to be part of the magnificent mystery we call existence. The quantum world doesn't provide final answers about the nature of reality, but it does offer an invitation to approach life with the kind of wonder and openness that makes genuine discovery possible. And perhaps that's the most profound gift of all, not the solution to the mystery of consciousness and quantum mechanics, but the recognition that mystery itself is the creative source from which all knowledge and all experience continuously emerge. In a universe governed by quantum principles, the deepest truth might be that reality remains forever open to new possibilities, new discoveries, new ways of understanding the relationship between mind and matter, between observer and observed, between the quantum world and the world of conscious experience. The paradox continues to unfold, not just in physics laboratories, but in the living laboratory of awareness itself, where every moment offers the possibility of recognizing something new about the nature of existence and your place within the grand, mysterious, endlessly creative dance we call reality. If you found yourself drawn into the mysterious relationship between observation and reality, you might enjoy exploring how these same principles reveal themselves when we examine the very thoughts that create our sense of self and world. I invite you to discover quantum reality reacts when you stop believing your own thoughts, where we'll explore how the simple act of re-examining our most basic mental constructs might open doorways to experiences that are just as strange and wonderful as anything we've encountered in the quantum realm. Perhaps the most transformative aspect of the quantum observer paradox isn't what it teaches us about particles or measurements, but what it reveals about the nature of knowledge itself. Throughout human history, we've equated wisdom with certainty, understanding with the ability to predict and control. Yet quantum mechanics whispers a different story entirely. The uncertainty principle, formulated by Werner Heisenberg, demonstrates that certain aspects of reality are fundamentally indeterminate at perfect precision. This isn't a limitation of our measuring instruments, or a temporary gap in our knowledge waiting to be filled by better technology. It's woven into the very fabric of existence itself. At the quantum level, reality preserves a space for genuine mystery, for possibilities that remain open even to the most sophisticated investigation. This principle extends far beyond the behavior of subatomic particles. It touches something essential about the human condition, about the relationship between knowledge and wonder, between understanding and humility. In a classical universe governed entirely by deterministic laws, everything would theoretically be predictable given sufficient information about initial conditions. Such a universe would leave no room for genuine creativity, for unexpected emergence, for the kind of novelty that makes life endlessly fascinating. But we don't live in such a universe. Instead, we inhabit a cosmos where uncertainty creates space for possibility, where the future remains genuinely open rather than merely unknown. This quantum uncertainty principle might offer a profound metaphor for understanding how to navigate the uncertainties of daily life with greater wisdom and peace. Consider how the most meaningful decisions in your life have often emerged from periods of not knowing. Choosing a career path, entering into deep relationships, moving to a new place, all of these life transitions require stepping into uncertainty with faith rather than perfect knowledge. The quantum world suggests that this uncertainty isn't a bug in the system, but a feature that makes growth and transformation possible. Some interpretations in psychology and contemplative traditions propose that the capacity to rest comfortably in uncertainty, what Buddhist teachers sometimes call don't know mind, represents a form of wisdom that transcends the need for constant mental control. Rather than viewing uncertainty as a problem to be solved, it becomes a creative space where new possibilities can emerge naturally. Take a moment to notice your own relationship with uncertainty as you listen. Do you find yourself constantly trying to figure things out, to nail down exactly what these ideas mean and how they apply to your life? Or can you allow yourself to rest in the not knowing, to let understanding emerge gradually, like dawn breaking slowly across the horizon? The quantum world teaches us that reality itself maintains this quality of open possibility even at its most fundamental levels. Perhaps learning to dance with uncertainty rather than fighting against it represents a form of alignment with the deepest principles governing the cosmos itself. One of the most remarkable features of quantum mechanics is how it reveals the universe to be fundamentally creative rather than merely mechanical. Classical physics painted a picture of a clockwork cosmos where the future was entirely determined by the past. But quantum mechanics introduces genuine novelty into the heart of physical reality through the unpredictable outcomes of quantum measurements. This creativity operates through what scientists call emergence, the mysterious process by which complex systems develop properties and behaviors that cannot be predicted from knowledge of their individual components. The phenomenon appears at every level of organization, from quantum fields giving rise to particles forming atoms, to atoms creating molecules, to molecules enabling life, to life evolving consciousness. Each level of emergence brings something genuinely new into existence, properties and possibilities that didn't exist at simpler levels of organization. The fluidity of water cannot be predicted from studying hydrogen and oxygen atoms in isolation. The capacity for flight in birds cannot be understood by examining individual cells. The phenomenon of consciousness cannot be reduced to the firing patterns of individual neurons, though it clearly depends on them. Quantum mechanics provides the foundational example of how emergence works throughout nature. When quantum systems interact and become entangled, they create collective properties that transcend anything present in the individual components. The whole becomes genuinely greater than the sum of its parts, not through any supernatural addition, but through the mathematical relationships that govern quantum correlations. This principle of emergence offers a profound way of understanding how meaning and purpose can arise in a universe governed by physical laws without requiring anything beyond natural processes. Complexity creates the conditions for new kinds of order to spontaneously appear, each level building on the foundation provided by simpler levels while introducing novel possibilities that couldn't have been anticipated from below. We've journeyed together through one of the strangest territories in all of science, where the simple act of looking changes what we're looking at, where particles exist in multiple states until observation forces them to choose, where reality itself seems to wait for awareness before deciding what to become. The quantum observer effect reveals that we live in a universe far more mysterious, interconnected, and participatory than our everyday experience suggests. From the double-slit experiment that first revealed particles behaving like waves until someone watches, to the instantaneous correlations of quantum entanglement that connect distant particles across the cosmos, we've seen how observation plays a fundamental role in the very fabric of reality. We've explored how consciousness itself might mirror these quantum principles, how the quality of attention we bring to any experience helps shape what emerges from that experience. Perhaps most profoundly, we've discovered that the boundary between observer and observed, between mind and matter, between the quantum world and the world of everyday awareness, is far more fluid than classical physics ever imagined. Every moment of observation, whether in a physics laboratory or in the laboratory of consciousness itself, participates in the ongoing creation of the reality we inhabit. As you carry these insights forward, remember that you're not merely a passive witness to the quantum universe, but an active participant in its unfolding mystery. The paradox continues not just in equations and experiments, but in each moment of awareness, each act of gentle observation, each recognition that reality remains forever open to new possibilities through the eternal dance between consciousness and cosmos.